So our next talk is from Keith Butler. So Keith is an Associate Professor for Computational Materials Chemistry at UCL, where he leads the Materials Design and Informatics group. His talk is on retention is all you get, but maybe that's all you need. So take it away when you're ready, Keith.
Thanks, John, for the intro, and thank you for the opportunity to come and speak at the AI Chemie webinar. So I'm going to talk to you a bit about some work that we've been doing over the last couple of years using concepts from language modeling to understand crystal chemistry and to help to design and discover new materials. And I think one of the take homes I'm going to give at the end of this is I think these are really powerful methods. I think a lot of what goes on with these really big models and the great performance they show is about memorization of data. I'm not sure these models are really learning anything profoundly new, but I also think that there's a lot you can do with that, and hopefully I'll be able to demonstrate that using these kind of concepts, there's still a lot of really interesting and useful science that we can do. So before I launch into the talk, because I'll inevitably go on too long, I want to acknowledge the people who did the work. So the main people to acknowledge are actually Cyprian and Lewis at the top there, who did the bulk of the work that I'm going to present in this presentation today, and a bunch of other collaborators who were also involved in that work. But before I jump into the language modeling section, what I'm going to start with is a brief introduction or a brief history of how I got involved with doing machine learning for material science and how I got into all of this kind of language modeling for crystals and so on. So it goes back to work that I was doing as a postdoc with Aaron Walsh back almost a decade ago now. And we were involved in doing density functional theory for materials design, and we used to do quite a lot of high throughput screening with density functional theory, trying to discover new sustainable energy materials. And while we were doing that, it's the sort of thing you start to think about is, well, just how many materials are there out there? And how many new materials could we actually discover with doing these kind of screening studies? And that led us to develop this code called SMACT, which is still under development today. So it's a code there's no real machine learning in SMACT. It's primarily a code based on chemical heuristics, but it allows us to do really fast enumeration of chemical spaces and to work out what kind of reasonable compositions might be possible when you start to mix together different elements in the periodic table. And so we just did that kind of thought experiment where we said we'll mix together binaries, ternaries, quaternaries in the periodic table, and we'll apply some kind of charge neutrality rules to that. So saying, based on the known oxidation states, can you form a neutral combination from those elements? And then also do some things about making sure that anything that's an anion in the material has a greater electronegativity than anything that's a cation. So things like Pauling's rules and stuff like that to kind of try and filter down the number of candidates. And you can successfully do that. So the plot on the left just shows applying these filters. And on the right, we've just plotted how the number of what we call SMACT plausible materials increases as you go from binary to ternary to quaternary. And essentially, you see exponential growth in the number of potential candidate materials. And at the bottom, I show the numbers of those same classes of materials in some databases. So in the ICSD and in Materials Project. So you can see the numbers there are in the regions of 10 to hundreds of thousands. So in the last, obviously this is from 2016, and in the last 10 years, that number has shifted. So you'll find the biggest databases now, you'll find things like Nomad and Le Material are probably up around the 10 to the 6, maybe between 10 to the 6, 10 to the 7 region, but it's still far short of the number of what we would think are plausible materials that we've predicted. So it's kind of really interesting. That's what really interests me in materials screening, is that if we could find ways to search that space, it feels like the answers to many of the challenges that we face are going to be in there. The materials that can do things like store energy better, or do better energy conversion, or trap CO2 and things like that. It feels like those answers might be in that material space. But as I said, I was doing DFT calculations at the time, and a kind of old calculation that I did back then was just to work out how long it would take to search through those spaces using DFT calculations. So I worked out that a single hybrid DFT calculation, which is what you kind of need to get accurate information on the electronic structure if you're interested in optical absorption, for example, takes about 24 hours on 512 processors. And I worked out, based on, at that time, the number of processors on the UK national supercomputer, that I could probably do about 230 materials per day if for some reason I were given all of the supercomputer to work on. Which, if we translate that to looking at just the ternary space on the previous slide, that's over 1,000 years to search through all of them. And I think that if we're relying on this kind of time scale to discover the materials that we need to solve our issues, then we're in a little bit of trouble if we have to wait 1,000 years to get the right materials. And I did also, the computers allowed you to do work out the cost of your jobs, and I worked out that this screening would cost roughly 5 billion, which sounds like a lot, but when you put it in the context of things like national deficits, which run at about 1 billion, over £1 billion per week, then it's only a month of national deficit in order to do this screening. So I think maybe there's some case that we can make to get all this computing to do this kind of screening, and it's a good investment. But assuming that we're not going to make that political case, we have to think of something else to do, and we have to find a more efficient way if we really want to screen through that space. And around that time it was kind of the time of AlphaGo, and a couple of years after ImageNet and ResNet had kind of or AlexNet had kind of started to break open the vision challenges, and deep learning and machine learning were kind of becoming quite high profile, and so I got really interested in that and thought, well, maybe there's something in there that we can use in order to tackle these problems that we're facing. And the first issue that anyone who gets involved with this kind of comes up against is that you have to have some way to represent your systems in order to feed them into the models, because the machine learning models are nothing except this function here on this big equation of there's some kind of function of an input which relates to a property. So this is if we're doing something like supervised learning. So where we want to predict, let's say, those band gaps that are so expensive to calculate, we have a function that maps an input to the band gap. The problem is, what is X? What is this representation that we put into our function? And we can worry about the function later, but what is X? And there are lots of ways to represent materials. Like chemistry is full of them. People come up with ingenious ways for centuries, but none of them are particularly well suited to being read into a computer. So we have to think about ways of building representations for feeding into the computer. And one of the first concepts that we come up against when we're interested in building representations is, do we want to use what's called a localized representation or a distributed representation? And so I illustrate these two concepts by this kind of schematic image on the left, where if we use a localized representation for these animals, then we essentially have one column within the vector that represents each of the animals. So if the animal is a bear, then the first column has a number 1 in it and everything else has zeros. And if it's a frog, then the final column has a 1 in it and everything else is zeros. And so you have one column per animal, and that's your representation. So you've got your set represented like that. It's called localist or a localized representation because all the information resides in one vector or one element of the vector. And we can do the same with elements in the periodic table. So if we want to represent compositions, we can just say if there's hydrogen and it's 1 0 0 0 0 0 and so on, and we can have a localized representation like that. Now, as opposed to that, you can have distributed representations. So in this case, the text might be a little bit blurry, but you have things like, you have columns that say walk, swim, fly, egg, claw, wild. And then you kind of give some numerical value to how much that property relates to the animal. So if we look at the bear, for example, the walk column is up near maximum. Whereas if we look at the fish, the walk column is down near minimum, whereas swim is up near maximum. Bear does a little bit of swimming, but not so much swimming. And so we get this distributed representation, which means that there's information in all the columns of the vector. And you can do the same thing with elements of the periodic table. You could think of that. And so you may think that this distributed representation seems a little bit more complex, and it's maybe a little bit less intuitive, but they have lots of advantages that make it kind of the way you'd want to go over a localized representation. So the first advantage is, well, let's say go back to our animal set. What if I came along and I added a cat to my data set? Well, now I'd have to change the representation for everything because I'd have to add a new column to the data set to be able to handle this new class cat. Whereas if I've got my distributed representation, it'll fit within the representation that I have. I just fiddle around with the values of the different columns. And the other thing that's really nice about this is that these distributed representations is that they give you a concept of how similar things are. So, for example, if I'd added cat to my data set and I looked at it in a localist representation, it's the same distance from everything because you just take the vector distance and it's going to be one in one direction. It's going to be one in all directions away from everything. So you've no idea how close they actually are or how related they are. Whereas if I look at them in my distributed representation, you'll probably see the representation for cat looks quite a lot like the representation for tiger, except maybe the column wild is a little bit dialed back. And that gives you this nice pattern of understanding how things are actually related. So let's say, hopefully I've convinced you, we want some kind of distributed representation. In the early days of the machine learning in material science, the way we used to construct these distributed representations was essentially we had a vector of a bunch of the properties. So like atomic number, electronegativity, so on, whatever properties you could get for the atoms, you put them into a vector. And then if you want to make a compound, you just add up the vectors in their stoichiometric ratios, and you have a distributed representation for the compounds. That's quite nice, but what we became interested in a couple of years ago was thinking about, are there ways that instead of putting in these kind of biases ourselves, are there ways that we could learn these representations from the data? And so we took inspiration from this work it's kind of classic work in natural language processing, which goes all the way back to this distributional hypothesis, which says that you know a word by the company that it keeps. And the example that I give all the time is this sentence here, where we say, Marianne saw a furry little whoppamink hiding in the tree. And so if you look at that sentence and I ask you what a whoppamink is, well, a whoppamink is a made-up word. So hopefully most of the people in the audience haven't actually ever come across the word whoppamink. But if I asked everyone to draw what they think a whoppamink is, you'd probably draw relatively similar representations. And the reason for that is because the context in which the word is turned up. And the kind of powerful idea here is that if we can just learn about the context in which words turn up, and we can see where they keep turning up, then we can learn something about the meaning of those words. And so how do we go about learning a distributed representation like that from the context of the words? Well, what we do is we use something called n-grams, which essentially you take a corpus of text and you take all the words that occur in it, and you create some localized representations for all the words that occur in your text. And then you feed it through this two-part model. So the first thing you do is you take your word. So in this case, I've got the word sans, like in this triplet of words. I've got the word sans. And from sans, I want to learn something about it from the context that it has. So I take the representation for sans and I put it through a neural network, which compresses it down into some lower dimensional space. And you can see the colors here are kind of representing that this has now become some kind of distributed representation. And then I try to use that distributed representation to predict the two context words. And so I try to predict the context words. Then because I've got training data, I actually know what the context words are. I checked whether my answer was right or wrong. If it's wrong, then I use the differences to update the weights of the neural networks. And I just keep running through my corpus of text like this. And eventually, when I've run through a large corpus of text and I've tried to predict all the context words of sans, then at the end of it, I end up with this vector that gets embedded for the word sans, and it's a distributed vector. And it's a distributed vector that's been learnt from the context in which that word turns up in the data set. So it's a learnt distributed representation that's gathered some information from context without me putting any kind of biases or prior information in. And so how does that relate to materials? Well, this is work we did a couple of years ago, and this was led by Lewis. So what Lewis did was essentially did the same thing as with text, except he converted the structures of the materials and materials project into graphs, and then got the nearest neighbors of all the atoms. And essentially from those nearest neighbors, then tries to learn a distributed representation for each of the atoms. So by trying to predict what the atom's nearest neighbors are. So it's the same thing I described before. You put in the one hot, you embed it, you use that to predict the neighbors, you train some kind of you use some cross entropy loss to train the weights of the network, and you just keep going around, and eventually you end up with a bunch of these distributed representations. And we can take a look at the distributed representations that come out. So these are the representations projected down into lower dimensionality. And the nice thing you can see here is that things that you would think chemically should be similar to each other are close together. So you remember I said a nice property of distributed representations is that they have some concept of similarity. So you see things like strontium and calcium are similar, fluorine and oxygen are similar. So, you know, they seem to have learned the chemistry that we would expect them to learn. But I always tell people to be a little bit cautious with these T-SNE reduced dimensionality maps. They're a little bit like reading tea leaves. As far as I'm concerned, you can start to see anything that you want to. So they're kind of a nice qualitative check, but I wouldn't trust my interpretation of it too much. So we also went ahead and benchmarked these representations on a bunch of problems. So when we benchmarked it against other compositional only representations, it's essentially state of the art. It does as well as any other and better than most. And in many cases, it's the best composition only representation. It even gets quite close to some representations that have an idea of structure. We'll come on to structure a little bit later. But embeddings really learn some chemistry that helps you with machine learning models. And then some work that was done by Anthony Onwuli, who was a PhD student with Aaron a couple of years ago. He extended that to think about oxidation states. So I won't go into it too much, but essentially you can, instead of thinking about elements, you can think about elements with a charge associated to them. And you can see that by doing this, there are certain tasks that this makes the models actually better for. So for things like predicting band gaps and the magnetism of materials, it makes quite a difference by adding this. And we can also use these representations to kind of do some mapping out of chemical space. So this is work, again, this was with Aaron's group, and this was led by Hyun-Soo. And we were just here thinking about a taxonomy of materials. So like things that are allowed by our SMACT chemical filters and are known in the databases are then things that we consider not super interesting. They're standard. If it's allowed by our filters, but it's not reported, then we call it missing. If it's not allowed by our filters and it's or if it's not allowed by our filters and yet it turns up in the databases, we consider that interesting. And then unlikely is if it's not allowed and it's not seen. And you can build some nice maps and get some kind of nice correlations between chemistry and those different categories. And one of the things we immediately realized from this was, if you look at this area of interesting materials, these are the ones that are not allowed by our filter, but do occur in the databases. They're mostly these kind of gray circles, which is unhelpfully labeled as others here, but others are generally intermetallic species. They're not oxides, chalcogenides, halides, or nictinides. And the reason it kind of led us to realize that a lot of these heuristic rules we used are not so good for intermetallics. They're actually really good for ionic systems, but not so much for intermetallics. And that's actually ongoing work to kind of try and develop new heuristics for intermetallics. But okay, so far I've talked just about composition, and the last talk was a really nice introduction to the importance of structure. So I won't go into it too much. But of course, the structure of materials determines its properties massively. So the canonical example here is carbon in two allotropes in graphene and in diamond. Like, you couldn't imagine two more different physically materials, and yet they've got the same chemical formula. So if we used a composition-based descriptor for these materials, you wouldn't be able to distinguish them. And so this leads on to some work that's been done by Lewis and Cyprian to try and use large language models in the area of generating crystal structures to go with these compositions. And it's all based on, it starts with this work called Attention is All You Need. So that's the kind of reference I was making in the title, which I realize some people might get, but if you're not au fait with the computer science literature, you may not get that reference. So Attention is All You Need is this paper which introduced the transformer architecture. It is, I think it was 2019 or so. And I mean, citations aren't everything, but I think this map of citations of a couple of important papers. So we've got the Attention is All You Need paper. This is the first graphene paper. This is the first hybrid halide perovskite solar cell paper. This is the venerable paper of density functional theory, just showing the sheer number of citations of this paper in a few short years is kind of incredible. Yeah, I did want to mention that these people didn't invent the attention mechanism. It's another thing that goes way back to the 1950s, and it's something that comes from applied psychology, where people were trying to work out why it is when you're in a pub or something, you can actually concentrate on the conversations you want to listen to, despite the fact that there's lots of other discussions going on around you. You can kind of zoom in on them. And what people were actually trying to solve when they developed this attention mechanism was this translation problem. So it was a classic problem of machine translation, where you're trying to go from English to French. So you're trying to translate this. The animal didn't cross the street because it was too tired. And what happened with traditional translation tools was that they translated the word it as L, which if you can actually speak French well, you'll realize is ridiculous, because L is the feminine, and that refers to the feminine object in that sentence is the street. And obviously that's ridiculous, because it's not the street that was too tired, it's the animal that was too tired. So you wanted to say ill. But the problem was that these translation models were biased by recency bias, what they saw last. And what attention essentially allowed it to do was to take in the full sequence and then pay attention to all the elements of the sequence and learn about the context of all the elements within this long sequence on an equal footing, and then decide how to do the translation. So that's basically what attention was trying to solve. And the way that people generally use attention now, and the way that we use it, is in this this kind of setting called next token generation. So with next token generation, what we do is we essentially take a sequence that we've had. So it's basically predictive text. You've had the last four, and you've, through your attention mechanism, your transformer, and your transformer at the end outputs a list of probabilities of what the next token is going to be. And then you take that next token and you compute the loss. So you work out, like, was that actually what the next token was? And you update the weights of the network based on that. And when you want to run it after training, all you do is you put in the start of a sequence, and then it just keeps going and generating the sequence until some point that it decides to stop. And around the time that ChatGPT came out, so this was, I guess, about 3 years ago or so, it seemed that there was lots of things using this next token generation. So people were using for all sorts of tasks, like generating images. So it seems like next token generation can do almost anything. And Lewis kind of came with this idea and said, I think we could use next token generation with a language model to do crystal structure generation. And I have to say, at the time, I thought it was a daft idea, but I was going on leave for a couple of months for paternity leave. And I kind of said to Lewis, well, feel free to waste your time if you want. And luckily, Lewis decided to go and do what he thought was an interesting idea, and he pursued this next token generation for crystal structure, prediction. And it's how he does it is it's essentially the same as the language models, except instead of training on the internet, he trains it on just a big set of CIF files, so crystallographic information files, and essentially tries to learn the content of the crystallographic information files. And then when you come to running it in inference mode, all you do is you prompt it with the top line of the crystallographic information file, and it just keeps generating next token, next token, next token until it hits 2 end of line tokens, and then it says, right, I'm finished. That's a completed CIF file that I've generated from you. And then you can look at that CIF file and check if the structural and chemical information is actually sensible. And I'll just give an example of the command line interface. Lewis has done a really nice job. If you're interested in the code, you can download it from his GitHub repo here. He's done a really nice job of making it very user-friendly. So, and you can just download pre-trained models if you don't want to train your own, and you can try it out that way. So then we kind of went and checked for the internal consistency of how this CIF generator was working. And I mean, I was kind of amazed by this, that, you know, things like the coordinates matched up with the space group that it suggested it should have. The site multiplicities were correct. We checked the bond lengths, and most of the time they're pretty reasonable. We also checked for a held out test set how often the structure that it generates matches the true structure of the material, and it's a pretty high number. So I should say we gave it 3 attempts, because just like GPT, it'll generate a different thing each time you prompt it. So on the first attempt, it gets nearly 80%. If you give it 3 attempts and say one of the 3, it's more like 85%. So I would say that when I first saw this, I was really amazed. I was slightly disappointed that I was totally wrong in my prediction that it was a waste of time, but I was really amazed by how successful it was. And just to say, you can kind of, if you want to, there's also a web app to go and try this out with. And this is a demo of the web app. I think you can see a video. So you just type in the formula to the web app here, and you can see it takes more or less long. It goes and fires up some GPUs, and then attempts to generate a structure, and then gives you the structure that is generated up on the screen. So if anyone's interested, that crystallllm.com site has the web app hosted there. But as usual with these things, like, you know, I remember when I first tried GPT, I was like, this is the most amazing tool. And now, what do I say about GPT? I complain that it makes too many M dashes. You know, we get used to it and we start expecting more from it. And we're getting into the discussion now of whether or not these language models for crystal structure generation actually learn something about the materials. And there's this debate about in the language model community in general, like, are they stochastic parrots or do they have a world model? And so by world model, I mean, if I'm predicting this sentence here, the glass fell off the table and I'm trying to predict the next word. In the world model scenario, what the model is doing is it has some knowledge of the chemistry, and it has some knowledge of gravity and what happens under gravity. And then it has some knowledge of how the chemistry relates to the mechanical properties of the glass. And then it makes a prediction on what's going to happen based on all of that. In the stochastic parrot version of things, it's just got a distribution of what the next token is likely to be. And it says that smashed is really highly likely, spilled is maybe more, is also likely, but less likely, and filled is very unlikely. So these two kind of opposing views of whether the models really understand something or whether they're just repeating the data set. And I think in the work, I'm going to skip the next slide, but in some of the work we did in that paper, so we tried to look at really tough materials. So one of the issues with the materials project data is that a lot of it's very similar to each other. So if it's a lot of the structure types are very homogeneous. So I think a lot of what it did actually is it's memorizing structure types and doing substitution within those structure types. So you find when you try to go on these unseen materials from the challenge set, the percentages that it gets right are really significant. They're still not nothing. They're still pretty impressively high, but it's not doing nearly as well as on the kind of the same distribution that it was challenged on. Another thing that we tried to do was to get it to generate low density SiO2, which I thought, well, if it really learns a world model, it would give us zeolites, but then it gives us actually these layered materials. But that's not to say that this isn't useful. So it's like ChatGPT, even if it produces lots of M dashes, it's still super useful. And what we've been doing lately with Cyprian is to introduce something called conditioning to the models, which I think takes it to the next level of utility. So just introducing conditioning quickly. So I took GPT and I asked it to give me the mission statement for the AI Chemie Hub. I gave it the website, and it came up with this mission, this brief, impactful mission statement for the AI Chemistry Hub. And I think that this is a pretty fair summary. You know, catalyze adaptation of AI, transform the chemistry AI interface, overcome key barriers with data and collaboration, and so on. So that's kind of the vanilla GPT. And then I tried to do it with conditioning. So conditioning is taking something like that and saying, well, generate me this this statement, but in this case I said in the style of Geoffrey Chaucer. And so now it's converted all of that into this kind of early English, in a kind of in a poetic meter, and it gives me things like to tame the wild forests of scattered data, which I think is actually maybe that should actually be the AI Chemie mission statement. But essentially, just to give you the idea that conditioning means that you basically take you're doing the same task that you were doing before, but whilst thinking about some other condition that you want to meet. And the work that Cyprian's been doing recently, and it's been released in this preprint, if you're interested, is to introduce conditioning to the CrystaLLM workflow. And just some examples of the conditioning. So this is just showing if you condition it on densities. So you've got the underlying distribution in gray, and then you've got different target densities that we want to target. And you can see that the distribution of generated materials really shifts based on this conditioning. And something that I'm pretty excited about is that we're now conditioning it on experimental data. So in this case, we're giving it XRD patterns and saying, okay, I'll give you a formula and I give you an XRD pattern now. And we can look, and you can see that the performance when you give it the XRD pattern is significantly better than when it doesn't have the XRD pattern. I think that's super useful because it's giving us a tool to help us to interpret experimental data. And then the final thing is, yeah, you can target utility. So this is kind of trying to make something that has optimal photovoltaic performance, and you can see the distributions again shifting around. Right, so I've got very little time left, so I'll just go with what I think are some of the big advantages of this CrystaLLM plus Pi is what we call it, Pi for property injection. So it's really lightweight and flexible. So as long as you can convert, as long as you can have access to a reasonable GPU, you can retrain these models. You don't need the kind of huge things that you need for training things like Llama, and the kind of the frontier LLMs. So it's only about 200 million parameters compared to the 4 billion of the really big ones. So it's a nice specialized model for materials. I like that about it. It's also really flexible, and you can condition on pretty much anything as long as you can convert it into a vector to condition the network on. So you can choose anything and do conditioning on it. It's also data efficient. Because we've done all this pre-training on these crystallographic information files, it means that you can fine-tune it with quite a small amount of data. So those crystallographic open dataset files that we use, we only use 1,000 of them to get those impressive results. Okay, so right at the end, so I'll just give a quick summary. So I don't think the singularity is imminent. I don't think we're reaching AGI. I don't think that these machine learning models are thinking like a person, but I do think that they're going to change things, and I think they're already changing the way that we do chemistry, and they can really accelerate how we do normal chemistry, like things like analyzing XRD, automating experiments. There can be a lot there, and they can also help us to learn stuff about chemistry by inspecting the models and how they work. And with that, I'll finally just thank you for your attention.